Excuse me. Sorry, I was facing some issue with my system. But okay, so final answer for this is 1.7. 1 second. Do it again. Plus 17.8 into 6 into cos of 15 into tan of 20 over 17.8 into 6 into cos of 15 into sine of 15. 1.78. And the height, the second part is height h, that will give the factor of safety 2 against the sliding along the rock. So let's say that uh, this h is not fixed. Okay, so we have in the same formula we will keep this as our variable and this as a given value. So we will have 2 equals 10 plus gamma h times, I think, yeah, cos square beta. Okay, cos square beta. One second. Let me check again. Okay, so cos square 15 into tan 20 over gamma h cos beta sin beta. Gamma is 17.8. So we will have 17.8 into 2 into cos 15 into sin 15. 8.9 equals 8.9 h equals 10 plus 17.8 into 7.8 into cos 15 into cos 15 into tan 20. So we will have 8.9 2.86 h is equivalent to 10, h is equivalent to 10 over which is 3.5. H is 3.5 meters. So for a depth h is equivalent to 3.5 meter, we will have a factor of safety of 2. And for a greater depth, we are having a lower factor of safety. Okay, so let's move on to the next part. The next part is we talked about definition of factor of safety, we talked about stability of infinite slopes. Now let's talk about stability of finite slopes. As I mentioned, that finite slopes can either have a circular, okay, I've not yet uploaded a question for this, that I will do it in a while, but it can have a planar failure or it can have a circular failure. When we have a plane failure, usually we use the Kalman's method, in which it's based on the assumption that the failure of the slope occurs along this plane, where the average stress, average shearing stress that causes the failure is greater than the shear strength. Okay. Um, so what we do is we take a trial surface and we take the weight and the reaction, just like in infinite slopes that we did. We do the normal component and the normal component and the tangential component, and based on that we get the value for just like in infinite slope we did, we calculated the normal component, the tangential component, then we took sigma dash is equivalent to normal component over, this will be this length AC. Okay, and tau will be the this component over along this AC. Okay. So then we take the factor of safety again as C plus sigma n tan phi over tau, and when we calculate, n comes out to be the weight of this wedge is the volume. How much will the volume be? This is h, half of base into h. But how much will the base be? Let's take only in terms of this AC length. Okay, this is theta and this is beta, isn't it? So if we take the weight of this wedge, it will be half of, let's call this A here, AC into H minus half of BC into H. No, BC no, AB into H, because we want to subtract this triangle. So we will get the area of this triangle, which actually is simply half of BC into H. But how we take BC? Let's take cos theta not a right angle triangle. Yeah, what we can do is we can take AC as h cos theta. We can take AB as h cos beta. Not cos, tan, should be tan. Tan beta is equal to h by AB. Tan theta equals h by AC. So AC is equal to h by tan theta. AB is equal to h by tan beta. So we will have BC equals AC minus AB h 1 by tan theta minus 1 by tan beta multiplied by half of h. So the area of this triangle ABC will be half of gamma h square, the weight. So this will be the weight after multiplying with gamma, 1 by tan theta minus 1 by tan beta. Okay, and next what we do is simply we what is the length? What is this length AC? AC will be, if we take sine theta, we will have h over AC. AC is h by sine theta. Yeah, this AC. Let's call this A dash because this is getting confusing now. This is not that A. This is A dash. A dash. A dash. A dash. Okay. A dash. Okay. This AC is h by sine theta, and just like in previous question, what we did was we calculated n by AC and t by AC. N was simply uh, this normal component of weight over to the failure plane. So we have W, it can be resolved as this. We will have, if this is theta, then this will be theta, this will be W cos theta, this will be W sin theta. Okay, so we will have W we have from here. We will have a W theta sigma dash will be W cos theta over H by sin theta, and we can replace the W, half of gamma h square, 1 by tan theta minus tan beta, 1 by tan beta into cos theta sin theta over H. This and this will go. So basically in the end what you will get is, let me write it in the next slide. You will get, for Kalman's method, and let's just give you the factor of sigma and tau and the factor of safety. Sigma will be half of gamma h sine of beta minus theta over sine beta sine theta cos theta sine theta, and tau will be half of gamma h sine of beta minus theta over sine beta sine theta into sine square theta, and your factor of safety will be so. Instead of finding the factor of safety here, what we do is, in Kalman's method, we can express the average shearing resistance or mobilized shearing resistance as CD dash plus sigma dash tan phi dash D. So we equate this and this instead of finding the factor of safety. If we take factor of safety equal to 1, for example, we will have half of gamma h sine of beta minus theta over sine of beta sine of theta sine square theta equals half of gamma h sine of beta minus theta over sine of beta sine of theta cos theta sine theta tan phi plus CD. Okay, CD plus sigma and tan phi. So we will have, if we take CD on one side, we will have half of gamma h sine of beta minus theta sine beta sine theta sine square theta minus, let's take one sine theta out, sine theta so we will have a 1 sine theta minus cos theta tan phi, and if we take one cos theta out we will get tan theta minus tan phi. And we can cancel these. Yeah, so that is what we get. Why is it on this slide? Okay, so we get CD is equivalent to half of gamma h sine of beta minus theta sine of theta minus, no, actually let's write it in a better way, sine of beta minus theta cos theta over sine theta into tan theta minus tan phi. Uh, so this is derived for the failure plane that we have considered AC. So as to determine the critical failure plane, we need that this should be minimum. So in this method, what we do is we take del CD by del theta and we equate it to 0 to find the minimum. So this will be del CD by del theta equals tan theta sine of beta minus theta over this is a tan theta into tan theta minus sine of beta minus theta over tan theta into tan phi half of gamma h. Del CD by del theta equals this and this goes. This will be minus cos beta minus theta and minus this will be tan phi tan theta minus cos beta minus theta minus sine of beta minus theta into sine of beta minus theta secant square theta divided by tan square theta. So if you equate it to 0, finally you will get a critical theta beta plus phi over 2. This will be a critical angle, and when we substitute this, we get gamma h by 4, 1 minus cos of beta minus phi sine of beta cos of phi. So what we do, we write this as C over gamma h, which is taken as the stability number, which comes out to be 1 minus cos of beta minus phi over 4 sine beta cos phi. And maximum height of slope for which the critical equilibrium occurs can be obtained by substituting CD equals C dash C and phi dash D equals phi dash in our equation, and from here we can get H critical is equal to 4C dash by gamma sine beta cos phi dash 1 minus cos of beta minus phi dash. This is the stability number. This is your critical height. So let's now Try to solve the second question, this question. This. I'm not able to erase this. I don't understand. Okay. No idea why it is like this, but let's continue. Okay, sorry. So we have been given a trial surface AC, and we have to determine the factor of safety for this trial surface. Let's try to do that. So average shear stress we just saw to calculate. It was half of gamma h sine of beta minus theta sine beta sine theta sine squared theta. If you calculate this, this comes out to be 10.48 kilonewton per meter square. And the shear strength is C dash plus half of gamma h sine of beta minus theta over sine beta sine theta cos theta sine theta tan phi dash. And if you calculate this, it will come out to be 32.3 kilonewton per meter square. So the factor of safety will be 32.3 over 10.48, which is 3.08. This will be the factor of safety. So it's a straightforward question. So now let's move on to the next part. I will just be briefly talking about these, and now we have finite source with circular failure. We can have a CU file or we can have a C5 soil. So then, what is wrong with this? Okay. So when the failure occurs in a way that the surface of the sliding intersects the slope, we have a circular failure, which can be a slope failure, it can be a toe failure, or it can be like a base failure. This is a slope failure, slope face failure. This is a toe failure, and this is a base failure. So in homogeneous clays with phi is equivalent to 0, what we do is simply we take the mass of the sliding body, if this is the circular failure surface, we take the mass of this body and we equate it W, and let's say this is the center of gravity and this is x bar. So we take the mass or the mass of sliding mass, weight of sliding mass, and we equate it to, let's say there is a unit cohesion, there is a cohesion Cu or not along unit length, Cu into arc length. We equate it to the cohesive strength along this surface. So what we get from this is CD is equivalent to W1 L1, where this is W1 and this will be W2, this will be L1, L2, W1 L1 minus W2 L2, because if you see here, this is actually some part, not all of it, but this W2 mass is, actually let me show it like this. Let me show it in a better way. Let us divide the wedge like this. This is weight 1 or weight 2. This is weight 1. This is L1. This is L2. So if you see the moment about O here is in this direction, whereas here it is in this direction. This is the disturbing moment while this is a restoring moment. So what happens is that this part of the slope actually is acting as a stabilizing part. That is why we are subtracting this here, and CD comes out to be r square theta. So factor of safety is then found as Fs is equivalent to tau F by CD is equivalent to Cu by CD, because we know for clay soil phi is equivalent to 0, tau F is equivalent to Cu. This is the factor of safety. So for C5 soils now, there is a general procedure. There is a general procedure, Arrhenius circle, which is called the friction circle method, in which we take this and we take a friction circle here. We make this wedge here. What we try to do, let's say that the resultant, this is W. Let us say the resultant is acting here. Uh, in this direction. We will join from the friction circle at this point. Okay. This will be the phi. This will be the angle phi. Not with W. Not able to draw it properly. Let me actually import the image so that I can show you in a better way. Let me not draw it. Let me just import it. So you have this slope. We assume the failure is taking place along AC. So we calculate the weight of the soil wedge A, B, C, the whole wedge, which is the disturbing force. Okay. Then what we do is we assume that the soil wedge has a CD unit cohesion along unit length is CD along this arc. Okay, so the total cohesion will be CD into the length of this arc. The length of this arc is R times this theta, R theta. So this will be CD into R theta will be the cohesion along this length. So what we do is we calculate the W and we calculate the W here and we draw a force vector, actual force vector to scale we will draw. Okay, and then what we will do is we will calculate the CD. We will calculate this total CD is small CD R theta, isn't it? And then we take this, and from here we join. We get the resultant force to scale. CD is the resultant cohesive force equal to cohesion per unit area developed times the area of the chord. So this acts, CD acts in parallel to AC. Okay, this is the direction of CD. We know the direction of W, we know the direction of CD. We know the magnitude of W, we know the direction of W. We know the magnitude of CD, we know the direction of CD. From here, we can calculate the magnitude and the direction of F, isn't it? So this F is basically the resultant force which is acting here. Okay. So from this F, resultant force or the normal and frictional forces along the surface. Okay. This is the resultant force. If we assume that full friction is mobilized, the line of action of F will make an angle phi with the normal to the arc. So if we take the normal here, normal to the arc, this will be phi. Okay. Now we can calculate phi, and from phi we can know how much friction has been mobilized. Okay. So this normal will be a tangent to a circle here. So what we do here is we make a 90-degree here. This will be r sine theta, and we make a circle here. Okay, this is the, excuse me. Because of the directions of WS, CD and F are known, magnitude of W is known, we draw a force polygon, and magnitude of CD can be determined from the force polygon. So the cohesion per unit level can be found, and then we use the stability number to get the factor of safety. Yeah, I know this lecture was a bit rushed, but that is the time that was allotted. Thank you very much. I think we can stop for today.